Yeah, thanks. Yeah, I understand that the title is a bit long, but yeah, I'll dive straight into it. This is one of many internal tide talks, so probably don't need the introduction, but I thought I'd show the slide anyways to underline that understanding where how much internal tide energy is created is important, because it's a crucial thing of the barotropic tide. We have local dissipation when the high modes break where they're generated, and then some of the high mode internal tides go into the ocean's internal wave field. That's a substantial contribution for the ocean's internal wave field energy. And then when these waves break somewhere far away from their generation site, they cause small-scale turbulent mixing that contributes to driving large-scale overturning circulation. So my point is, it's important that we figure out where how much internal tide energy is generated. And we have several methods to do so, and one is based on linear theory. As the name suggests, then you only have the linear part of the problem, and you need to ensure that when you use linear theory that the underlying linearity assumptions are met, which is not that straightforward. But the advantage is that you can follow a more or less straightforward procedure at relatively moderate computational cost. And linear theory is based on the work by Bell, and he considered an infinitely deep ocean, and his expression were then updated to an ocean of finite depth by Llewellyn, Smith and Young and Katiwala. And the main effect of having also an upper boundary is that you now generate discrete vertical modes of internal tides. And another effect is that the generation is maximized for those cases where the topography wavelength matches that of the internal tides. And here at the bottom, I'm showing two examples of previous computations using either a variant of the Bell formula, that's Jonas' results for the non-modal M2 tide generation. And then on the right side, his back then PhD student, Said Falahat, he took the expression by Llewellyn, Smith and Young and computed the generation of the different vertical normal modes. And as you can nicely see, we have a lot of generation at interesting topography like Y or other ocean ridges. You have intermediate values along the mid-ocean spreading centers and very low values over the abyssal plains. Right, and what all these previous estimates have in common is that they estimated the internal tide generation roughly in the way that they integrated over the source density, where the source density is a more or less complicated function, but the main point is it includes the barotropic tidal currents and the topography gradients. And the point is that the tidal currents and the topography gradients in reality, they have a direction. And as you can hopefully imagine, that if you have a topographic ridge and that's oriented somehow, it matters at which angle the tidal currents cross this ridge for how much internal tide energy you create. And this part is not included, or this piece of information is not included in these previous estimates. And now we argued that one could consider the equivalent expression and calculate the conversion as a line integral around the source area over the energy flux. And from, among other things, from this equivalence, you can estimate the energy flux. And that's the quantity with the direction resolved that we're interested in, because then we also have the effect of the directionality of the barotropic tidal currents and the topography gradients included here. And in this talk, I'm not going to talk about this theory. What I'd like to show is what we get out of it when we apply it to the global ocean. And I consider the first mode of the M2 tide. But before I'll show nice colorful maps of this, I would like to come back to the point that I made before, that one disadvantage of linear theory is that you have to make sure the linearity assumptions are met. And one of the main linearity assumptions is that the slopes of the bottom topography need to be less steep than those of the tidal beams. Otherwise, linear theory is invalid. So we have this supercriticality parameter gamma that measures the ratio of these two slopes. And if it's less than 1, we call them subcritical slopes. This is where linear theory is valid. And when it's increased to 1, it's critical, and then larger than 1 is supercritical slopes. And this is where linear theory breaks down. And typically the approach is you apply linear theory everywhere in the global ocean, and then afterwards you figure out where the supercritical slopes are and you somehow correct for this. And Angelique Millet and her co-authors suggested that everywhere where the supercriticality parameter exceeds unity, one could divide the total conversion by this parameter squared. This is based on the observation that in the linear regime, the conversion scales with the parameter squared. But then as you increase it to the nonlinear regime, there's some saturation. And this would not be seen by the linear theory. So essentially it would overestimate the conversion at supercritical topography and needs to be kept somehow. And what I'd like to do now is revisit this idea for two types of topography. One is representative of the isolated ridges and seamounts we have in the open ocean, and the other case is for continental slopes. So now here we consider the conversion at a one-dimensional Gaussian ridge, just as this exponential function. I'm showing the scale conversion as a function of the horizontal wave number of the mode 1 times the topographic scale. Each line represents a different mode. So red is mode 1. This is what we want to focus on here, right? I will show the results for mode 1. Blue is mode 2 and green is mode 3. And this is moderately steep, where the height of the ridge is 20% of the water column, and this is already pretty steep, where it's 40%. And these black lines show you where linear theory is invalid to the left and valid to the right. And now what you can see is that for the first mode, the bulk of the conversion is where linear theory is actually valid. But as the topography becomes steeper and steeper, this black line moves to the right, meaning that more and more of the conversion will be in the regime where linear theory breaks down. But as long as the slopes are not too steep, for the low modes, this supercriticality is not really an issue. And then, well, there are no analytical solutions for the nonlinear case, but there are some estimates for idealized topography, and we can look at them to get an idea of what the true solution left of these black lines is, where linear theory breaks down. And we use the estimates of a conversion at a wall by Llewellyn, Smith, and Young. Those are the dashed lines here, to get an idea of what the true nonlinear solution should be. And you see that here for the moderately steep case, the nonlinear solution is for all three modes higher than the linear curves, meaning we don't have an overestimation by linear theory in this case. Over here, it's actually not true for all modes. So for mode 1 and mode 2, this is still the case, but for mode 3, this dashed line is below the linear curve. So here's one scenario where linear theory might actually overestimate the true solution. But for the mode 1 that we want to look at, supercriticality is not really a serious issue. So that was for the open ocean, for an idealized ridge. Now we look at a sharp step to represent continental slopes. So you use this arctangent function to describe it linearly. And then there's also an estimate for the nonlinear solution, in this case by Saint-Laurent and his co-authors. And here you see again the scale conversion as a function of the topography height over the total water depth. The red line is the linear solution, and the black line is the nonlinear solution. And you see that as long as this ratio is not super small, the linear solution will be below the nonlinear one. And another issue is that the nonlinear solution has a step has a deep side and a shallow side, and the nonlinear solution can differentiate between that. So the deep side is the green line, and the shallow line is the blue line. And you see that they're very, very different. And the linear theory cannot distinguish between those two aspects. And we want to resolve the direction of the internal tide generation. So at some point, we will be pointing toward the deep side, and at some point, we will be pointing toward the shallow side. So it's a bit problematic that we can't differentiate between that. So the conclusion for the continental slopes is that here again, linear theory is not doing a good job, but capping will not really resolve this issue. And it doesn't differentiate between shallow and deep sides. But we don't really know how to deal with this. So our argument is that it's better to exclude the continental slopes completely rather than keep them in and not knowing how to correct for the fact that linear theory will not do a good job there. So what we did is that we built a mask, well, for land, obviously, but then also for the continental shelves, for the continental slopes, and also for deep ocean trenches, which likely need to be excluded as well for similar reasons, but that mainly affects the trenches here in the North Pacific. This is based on the geomorphology data of Harris, and now, well, afterwards we had to do some manual correction. What I did mainly was to mask the entire Mediterranean Sea and add this continent of Zealandia here. But basically this is now the map, and I will only compute the conversion in the unmasked blue areas. Right, and this is the result. It looks pretty similar to the maps we've seen before, right? So we have large generation at interesting topography and very little over the abyssal plains. But what this method can do is resolve the direction. So we're going to look at this. And what I did now is, so the map before is the conversion, so the energy flux integrated around the entire circle. And what I'm doing now is that I integrate only over a small circle segment, an angle increment of approximately 4 degrees around north, around northeast, northwest, or west. And what you can nicely see is that the conversion changes depending on what direction you look. And I'd like you to focus on, in particular, on hotspots of internal tide generation that we see in these other maps, because it turns out, maybe not that surprisingly, that they're not hotspots for all directions. So if we look at the Iso-Bonin-Mariana arc system over here, that's basically elongated in north-south direction. So we have a lot of generation in directions that partially or to some extent cross it, but in the direction that's along the ridge system, we have very little generation, and the same holds true here for Hawaii. The ridge is, well, roughly aligned in east-west direction for the island chain. So we have a lot of generation by the Hawaiian Islands, but this is only in directions that are, to some extent, not aligned with the ridge system itself. Right, and then finally, a comparison to previous estimates. On the left is our new method, and on the right is the result by Said Falahad. And the geographic pattern, I would say, agrees nicely with what he got. Our map is, however, much smoother. This is because we considered really large topographic patches surrounding the point of interest to compute the generation, because it's a non-local problem, and we take a lot of surrounding topography into consideration when we do the computations, and his method is more relying on the local topography gradient, so it will be less smooth. But a really interesting difference is that the global integral is, in our case, much lower. They get 212 gigawatts roughly, and we only get 83 gigawatts. And the main reason is that we have the mask at the continental shelves, right? So if you apply our mask to their results reduced by a factor of 2. So it's only half of their conversion is in the open ocean. The other half is on the continental slopes and shelves. And the story is the same when we take a different data set. So I also checked for the 4-kilometer HICAM simulation. They have 221 gigawatts of mode 1 M2 tide generation, and this reduces to 150. So this is a third less, roughly, when we apply the mask to their data set. Said Falahad also checked for supercritical slopes. He used the equation that I've showed, and he found that 55% of the conversion occurs at slopes that are supercritical. So this is almost the number of the conversion that is removed when we apply the mask. So basically the mask accounts for the majority of the supercritical slopes. This is nice because that's why we were using it. But then if you then use a capping instead of the mask, it will be applied at the continental shelves and slopes mainly, where capping won't really solve the issue that linear theory is not doing a good job. So this, well, the bottom line is really that we need to figure out how to treat continental shelves and slopes in linear theory estimates of internal tide generation. And if anyone has a good idea, I'd be super interested to talk about this. And now, for the remainder of the talk, I wanted to show you what happens when we use this directional tidal forcing in the internal wave model EDMX. So EDMX is based on the radiative transfer equation, which you see up here. Shows the rate of change of spectral energy density, and it has the propagation, it has the refraction, it has the generation, wave-wave dissipation, wave-wave interaction and dissipation terms. That all goes in there. What you have to do is that you feed EDMX with external forcing functions that tell you how much internal wave energy is created from the tides, from the winds, and from eddies. And what EDMX gives you is the dissipation of internal wave energy, which you can then use in a TKE model, say, use the Osborne relation to get the diapixnal diffusivity. Right, and we had previously used a different tidal forcing, and now what I'm doing is that I'm using the directionally variable one that I've just shown you. And for that, to do so, I need to use an update of the EDMX model, which is a compartment model. So there's the high mode continuum, and then there's compartments for the low modes. That includes the near-inertial waves that are generated by the wind and the M2 tides. And the low modes they are resolved in wave number angle space. So they propagate with a certain direction. And then the total internal wave energy is the sum of them, and the high modes will then break and dissipate and give their energy to the TKE scheme. Right. So what I'm using for the low mode forcing is then, well, the winds, I don't touch that. I keep that as it was before, and the directional tidal forcing that I've shown. And for the high modes, I keep what we used previously. I just reduce it by a certain factor. But I mean, there's modes higher than 1 for the M2 tide, and then there are other constituents. And to make sure that Eddy also gets that information, I needed to use much of the old tidal forcing. And now I'm comparing two simulations. One has the directional tidal forcing as I've just shown it. And then to mimic the previously isotropic tidal forcing, I just used the average energy flux in all directions. So the total conversion that I put in is the same. It's just that one varies with direction and the other one doesn't. And what I'm showing here is the ratio of these two cases. So it's anisotropic versus isotropic scenario. On the left-hand side is the M2 tide energy. And on the right-hand side is the turbulent kinetic energy dissipation rate between 300 and 1,000 meters. And what you can nicely see is that it has a large effect, that resolving the direction of the tidal forcing has a large effect on the M2 energy. So in directions that somehow cross the Hawaiian Ridge, there's much more energy than before. Along the Hawaiian Ridge, there's less. Also for the Mariana Arc system, along it, there's less energy. Across it, there's more. I was a bit disappointed that the effect on the TKE dissipation was not that noteworthy. So the color scale here is a factor of 2. The color scale here is only 10%. But that doesn't really mean that it's not important to resolve the direction of the tidal forcing. I think I had only mode 1 in there, right? So as a test, I put in modes 1, 2, and 3. And you can see that the effect on the TKE dissipation rate increases already. So I guess when we resolve the directionality of the higher modes as well, then it will be really important to include this also for the vertical mixing in the ocean modeling. Right, and I'm not sure how I'm doing on time, if I need to skip, well, okay, I'll skip the summary and take questions.